from Caltech now. We will talk about the classical polytime algorithm for finding ground states of 1D gap block of imaginary. Wait, is that the inversion?
It's a variant.
It's a variant, okay.
Yeah.
Okay, all yours.
I guess. Probably.
Oh.
I guess for some people this doesn't make any difference whether I write that or not, right? But I guess to me it makes a difference. So this is joint work with Zef Landau, Umesh Vazirani, who are both from here. And everyone can hear me fine, right? Okay. Let me just very briefly set things up. So we're going to be talking about a 1D chain of qubits. Qubit. So each qubit or qubit is going to be a d-dimensional system. And I have n of them. So I label them from 1 to n. 1, 2, 3. In general, one in the middle I might call I, and then up to n. So that's our space. And on that space, we're given a local nearest neighbor Hamiltonian. H. So it's a sum of local terms, H1 up to Hn minus 1, right? So H1 acts on the first two spins, H2 acts on these two spins, like this. So it's specified to us. There's normalization conditions. Just for simplicity, I'll assume that each of these terms is positive and also has norm at most 1. And now this Hamiltonian has a ground state, right? So for the ground state, I'll write it as gamma, and it has energy that I'll call E0, so it's the minimal energy, gamma H gamma. Okay? And we're also given a precision parameter, delta. And the goal is to find a representation, efficient representation for something that's kind of close to gamma. So find, in this talk, so I guess I don't need to introduce matrix product states for anyone. So find a matrix product state representation for a vector gamma tilde such that these are close. So gamma tilde, gamma is at least 1 minus delta. So delta is just my approximation. Think of it as a small approximation parameter. Right? Small constant actually could be even inverse polynomial in the length of the chain. Okay, so the question is whether we can solve this problem, right? So that's the problem. So the first question maybe should be, I should say question is, does this representation exist? So does there exist a efficient polynomial size representation for the ground state? So does a small, let's say, polynomial size. So when I say polynomial, it'll always be polynomial in the length of the chain, right? The number of qubits. That's the parameter that grows. The local dimension d is fixed. Like think of it as being 5 or 10 or something like that, right? So does a polynomial size representation for the ground state or a good approximation to the ground state exist? And so the answer,
yes.
No. No. So far this problem is QMA hard. So if you believe that QMA is bigger than NP, there's no polynomial size representation. Problem is QMA hard. It's QMA hard even in this setting, right? So I have a one-dimensional Hamiltonian. It's local, nearest neighbors. If my dimension is at least 8, right? So this is what Sean. So this is a result by Sean Halgren, Daniel Nagaj.
Are you already assuming gap, or?
Did I write gap?
Oh, so you're
right.
not. Because I was
So
looking
I'm
at your
not,
title. That's why I thought.
Right. So not yet. So that's
Okay,
why.
fine.
Exactly.
Then
So
it's
if I'm at that level of generality, the problem remains hard. Right, it's a hard problem. It's just too general, right? I haven't put any structure on my Hamiltonian except the 1D local structure. So what I just wanted to say is that if we state it in this way, we're not going anywhere. Right? This is just impossible problem to solve.
Does QMA hardness have to do anything with existence?
Yeah, if you believe that QMA is different from NP, then it's saying that the problem there's QMA hard. It's not in NP, so there's no witness that you could efficiently verify. No classical witness. This is what I meant.
But for the non-existence, so the non-existence is just a mathematical theorem. Say here is a Hamiltonian that does not exist.
Exactly. So if QMA is different from
you
NP,
can prove it without any complexity theoretic assumption.
I could potentially, but I don't want to prove it.
This Sanji-Rodney construction, for example. But it's
Yeah,
volume
so-
scaling of entanglement, so.
Yeah, exactly.
probably,
No, but that's right. But that's if you look for. It depends. Then you have to. I don't want to get into this. I mean, then you have to say what you mean by a representation.
No, MPS. Oh, only for MPS.
No, but
MPS.
only for
That does not
MPS,
exist in
yes.
MPS. Okay, so sure, yeah. So the answer is just okay. Right. So the answer is no under no assumptions. Yeah. Okay, thanks. All right. So we need a little more structure. So the one natural structure to impose is that I'm going to impose is that this Hamiltonian has a gap. So there's a unique ground state. Unique ground state, and then there's an energy gap above this ground state. So there's a gap. So I'm going to have the first excited energy, E1, and E1 is at least E0 plus some gap delta, and delta is a constant gap that's independent of the system size.
So if we have a critical system, you know, an ordinary system, critical system with a log growth in the entanglement entry, that would still be polynomial with the usual algorithm.
What would be polynomial?
The computation time for a DMRG like.
Well, as far as I know, DMRG, there's no bound on the computation time.
There's no rigorous bound, right? But
Oh, you mean
usually
DMRG
think-
would
we
still,
usually
you'd
think
expect
about
it.
how, you know, the entanglement grows, the MPS grows in a polynomial, you know, the M grows in a polynomial
Yeah,
fashion, and so it's still polynomial.
yeah. The size of the.
So I'm just wondering if the, you know, you proved it for the gap case, but could you also prove it for a log growth?
Yeah, that's a good question.
Potentially.
That's a good question.
The question is if delta is in the order of 1 over n,
Yeah.
what will... is it
It'll be very
simple?
bad, I'll say it in a moment. So the dependence on, right, if you allow delta to even moderately go to 0 with the system size, at least what we have is not going to perform well at all. I'll say precisely.
It's exponentially in the gap, right?
It's doubly exponential.
Oh.
It's very bad. I'll say it in just a minute. Or we could skip to it. I mean, okay, does a representation exist? The answer is yes, right? So that's Hastings result. If you have a gap, I mean, in our setting, what that result is saying is that there exists the MPS for this gamma tilde here of size, or I could just say of bond dimension of size polynomial in the length of the chain and the approximation. So this matrix product state exists, and the question is, can you find it? So this is question 2, I guess. Question 1, question 2. Can you find it? And I guess Steve gave the answer. The answer is yes. You know, DMRG finds it. That's what DMRG does, right? So yes, DMRG finds it. Except maybe it's not so clear, right? So in practice, it finds it. In theory, you can come up with examples in which DMRG gets stuck, contrived examples in which DMRG gets stuck in local minimum. In particular, there's a nice result by people here, or some of them are here, Frank, Norbert, Ignacio, showing that in some cases you can have an artificial construction of a local 1D Hamiltonian like this, such that there does exist a polynomial size matrix product state representation for the ground state. But if you could find it, then you could also efficiently factor numbers, so which we don't know how to do. So presumably, there are cases in which this exists, but it's presumably hard to find it. So these constructions are artificial, and in particular, they're not gapped, right? These systems. So, but what this is saying is just that the fact that there is a representation doesn't imply that I can find it. I'm going to have to use the structure of the problem. So that's, this is background for everyone. I think everyone is sort of familiar with that. So
did you just mean to say no, the MRG may not find it?
Yeah. This was, well, it depends who you ask, right? So if you ask Steve, I don't know. If you ask me, I'll say.
Okay.
No, I know there are hard things.
In the context of this talk, then the answer, well, can you find it? No, DMRG doesn't. Our algorithm finds it. So
Okay, so it's a yes, but not the DMRG.
Yes, so I guess that's the point of this talk is to give an algorithm that always finds it in this context, in these assumptions, right? In polynomial time. So this is what I was going to say. What's the result that I want to present? So I'll write theorem, so then we know the difference. So theorem, there is a polynomial time algorithm. So there is an algorithm that finds matrix product state representation for this approximation gamma tilde in time polynomial in n and 1 over delta. So it runs in polynomial time, provided the gap and the local dimension are fixed. So then the question that Jens was asking is, what's the dependence on the gap? Okay, this is pretty valid. So I have to say, what is the exponent here? It's a constant exponent as long as all the parameters are constant. But this exponent is 2 to the, then there's a polylogarithmic dependence on the local dimension, and the gap shows up here, right? So this is a comma here. So if you want a certain precision, this is pretty good. It's going to be polynomial in the precision that you want, but the gap shows up in the exponent of n. So it's not the exponential in the gap. What this means is that if delta even goes to 0 as 1 over logarithmically fast, you have an exponential time algorithm. So it doesn't do well at all. Not good.
But is it exponentially better than the bolts that Hastings had?
No, not in delta, in small d. The dependence on small d, right? So the dependence on small d just relies on how good the array laws are, and so this dependence is a dependence that comes up from the paper by Arad, Kitaev, who mentions it, and it is exponentially better than.
So the delta is error in total energy or in energy per site?
Sorry?
Is delta is error in the total energy or energy?
It's actually error. In that case, you could get both, because you can really think of delta as being 1 over n squared or something. So delta is much smaller than the length of the chain. So it's let's say total. I mean, we can get total. I mean, the way I phrased it is just how close you are to the actual ground state. So if I write this, then it's going to be energy per site. I mean, the total error in energy could be n times delta. I'm going to be off n times delta in energy. But I can choose delta to be 1 over n cubed if I want. It's the same algorithm. So, other questions? I can vary d, but it's going to scale very poorly with d. So I'm thinking of d as being fixed. That's how I think of it, yeah. But if you vary it, the formula holds. But if you want something that's efficient, you should think of d as being fixed and really small.
Maybe one comment.
Yeah.
If you have a translation invariant system, looks like a not bound. This delta is a very strict bound. Because for the large system, the overlap wave function can be rather small, even though the locally wave function is very, very close.
Yes.
So here you require the whole wave function
Yes.
overlap near 1. So that's very, very strict.
Yeah, so right, so so I'm not assuming it's translation invariant. So if you had a translation invariant system for which you are really thinking of the chain as being infinite or semi-infinite, then you'd have to phrase your goal differently. I agree. You'd have to say, I want to approximate the energy per site and not.
But in that case, you get a better, in a quicker algorithm.
Yeah, we didn't quite study that question. I think it's an interesting question. We were talking about it the other day. We're not quite sure. So the goal for the talk is to get a little bit into that, like give you the ideas that go into the algorithm, how it works. Not so much because I expect many of you to go home and want to implement the algorithm, but because I think that there's a couple nice ideas that go into making this work. These are ideas that use the structure of the problem in a certain way, right? So I have a structure which is it's one-dimensional, local, Hamiltonian, and then there's this gap. So there's a couple tools that we introduced that make use of this structure of the Hamiltonian in order to devise the algorithm. And I think these tools could be useful in other contexts, right? So the main goal is not necessarily to have an algorithm that you can implement, it's to go further than that, apply these tools to other problems that some of you may be interested in, like maybe time evolution, or maybe Gibbs states at some temperatures, or maybe two-dimensional. Some of the tools crucially use the one-dimensional structure, of course, and some of them don't, so maybe they're interesting to study the two dimensions. Okay, so I want to give you a picture of what the algorithm does to start with, and then I'll say a little bit more details. So it's going to be, at a very high level, it's a little bit like DMRG. It's going to be an iterative algorithm. So what we're looking for is this approximation for the ground state, this matrix product state representation, which is something that looks like this, right? It lives on the whole chain. And we're trying to find this object, and we're going to construct it iteratively proceeding from left to right. So I'm going to first construct tensors that live on the first qubit, then on the first 2 qubits, the first 3 qubits, etc., until I arrive at the end of the chain. DMRG does this a little bit, but it does a local optimization of each tensor, keeping one matrix product state, and it sort of goes back and forth. We're only going to do one pass, so just go from the left to the right. But one difference is that I'm not going to maintain just one candidate solution that can be extended to ground state. I'm going to maintain a huge bunch of candidate solutions. So I'll maintain a lot of partial matrix product states on the sites up to I, among which I know I can find something that, when I go all the way to the end, will give me my good approximation. But I maintain this whole set of vectors, and I sort of drag it along. So to explain how this is done, Zeph has a nice metaphor that sort of thinks of this algorithm as walking on an icy lake and trying not to fall through the ice. But then I thought, given the weather, this strategy is not going to work. So I have another metaphor to give you for what the algorithm, how the algorithm works. Is a classic metaphor of the needle in the haystack, right? So this is the problem that we're trying to solve. We're trying to find a needle in a haystack. The needle is the ground state, and the haystack is the space of all possibilities, right? All possible matrix product states. And we're going to have this needle in this haystack. And think of this haystack as something that we're going to drag around from the first qubit all the way till the end of the chain. So when I start my day, it's easy to set up a haystack that contains the needle. What's the needle? The needle is some matrix product state here that can be extended to a good approximation to the ground state. I want to construct a haystack that's guaranteed to contain that needle. Well, that's easy because this is a very small space, right? This is d-dimensional. I have my real law, so I have a bound on the size of this. So I can just take sort of a epsilon net or all possible candidates. I take all possible pieces of hay that live on that space, and it's guaranteed to contain my needle. The needle is whatever will eventually lead to the ground state. So I can get started. I have the haystack, the needle. And I'm going to proceed from left to right, including more and more qubits, and growing the size of this haystack to make sure that I always contain the needle. I always contain the left half of something that can be extended to this gamma tilde. Yeah?
What do you mean on the state on the first? So you are tracing out the rest, or what?
No, I'm considering objects that look like this. So tensors that have one physical index when I start, and one logical index here that has a certain dimension b, which is as large, let's say, as it needs to be, given the area law. So that's what I have. My haystack when I start the day contains objects that look like this. And then the second day is going to contain objects that look like this. And the third day, objects look like this. And of course, the sort of obvious problem is that as you drag haystacks, on the ground, they pick up more hay and
Yeah. So how does your size of the haystack grow with?
Yeah. So this is the metaphor step. But obviously it grows, right? Obviously it grows, and this is the main problem we're facing. Even if it grew just moderately, right, by a factor 2 at every step, I continue this. By the time I end here, I have a haystack that contains a needle. The haystack is exponentially large. Okay, I haven't achieved anything, right? Of course I have an exponentially large space. So this is where you need ideas, right? So, and that's where there's a couple interesting ideas that we're going to introduce. So there's two procedures that we introduce that keep the size of this haystack under control. So that when we arrive at the end of the chain, we still have a polynomial size haystack that contains the needle. And then we can find it, because when we arrive at the end, we have a way to characterize the needle, right? It's just a state that, let's say, minimizes the energy. So this is how we find it in the haystack, provided the haystack is not too big. So how do you keep things under control? So there's two procedures. One is pretty simple. You have a haystack, it's too big, you want to make it smaller. What do? You put it on fire, right? So the first idea we have is that, I mean, I'll show you in more detail what this means, but the idea is that if you arrive at a certain step and your haystack has grown too much, you want to reduce it, you light it up, light it on fire. And this will reduce the size of the haystack, and because the ground state is a needle, it's in metal, it's going to stay in the haystack. So that's pretty straightforward. So this step is going to use, well, I'll just say this is going to use the one-dimensional structure in a key way, right? Also the gap, but the one dimension. Okay, we have another problem, which is that if I do this all the time, so I proceed through the chain, and I keep lighting it on fire to reduce the size, what's going to happen? I mean, this needle is getting hot, right? And if I do it too often, the needle gets hot and hot and hot, and the hot needle, what happens to it? It gets bent. So the quality of my approximation, the needle, the approximation gamma tilde, or partial approximation to gamma tilde I'm dragging around, is going to decrease very fast as I keep. So that's the cost of keeping the haystack size under control. So I need another procedure to maintain the quality of the approximation. And so that's a procedure that I need to combat the effects of the fire, of the heat. So what are we going to use? Ice or a fridge or something like this. So let's say ice, let's say fridge. Let's say fridge. So this is kind of a cooling down procedure that's supposed to combat the effects of the fire. And this is how the procedure is going to go. You're going to make a few steps. This haystack set of candidate solutions is going to grow up by too much. You want to put it on fire. This has the risk of messing up the quality of the approximation too much. So first you cool it down. So first there's going to be a procedure that increases the quality of your approximations, makes them better. If they're delta, they become better than delta. This is what I call sort of cooling down, solidifying the and then we're going to heat it up, get rid of the extra hay, and then continue until the end we have a polynomial size haystack. So that's the idea. Is it clear? Okay. If it's clear, I guess there's a wine reception outside. So okay, so now let me give you a little bit more details, right? I want to be a bit more substantial, but this was just maybe something that you can hang on to as I give you the more details. Maybe it was helpful, maybe not. Maybe it was entertaining, maybe not. Who knows? So because we're serious now, we're going to stop this fast with ridiculous language and use some much more fancy terms for everything. So the needle, this I told you, right? This would be the ground state, or actually it's what I'll often refer to left half MPS. Right? So where the left half MPS is really the kind of object I was drawing here. It's a matrix product state that lives on the first I sites, and it has an open bond on the last side. So the haystack, we have a very fancy name for this one. It's going to be called the viable set, and I'll explain what a viable set is. Fire is something that we call decoupling. So this is going to use the one-dimensional structure, the decoupling procedure. And the fridge is an interesting object that's called approximate ground state projection. This is going to be some kind of an operator that you can apply to your vectors in order to improve the quality of approximation that you have so far. So I'll explain all of these. And so first I'll give the main definition, which is this haystack, so viable set. Definition. So what's a viable set? So it has 4 parameters, but that's about as much parameters as there'll be in the talk. So we're going through them. So there's a qubit index, there's a quality parameter, delta, and then there's 2 size parameters. One is a bond dimension parameter, and the other is a size parameter. Viable set, and I'll call it usually SI. So what is this? It's just a bunch of tensors like this on I sites. So a set of them like this. So it goes up to I1. Each of these legs is d-dimensional. This one is, actually there's not going to be, I'm sorry, here I'm just going to stop like this. On the first I sites, such that the size of the set is S. The bond dimension of these vectors is at most B. And the important property is that the haystack contains the needle, right? And what does that mean? So, and gamma tilde, or some approximation to the ground state, so there exists some gamma tilde such that it's a good approximation to the ground state. And if I look at the reduced density of gamma tilde on the first I qubits, so I'm tracing out I plus 1 to n of gamma tilde, this reduced density matrix is supported on the span, so the linear span of this set Si. Right? So it's worth parsing the definition, right? So I just have a set of vectors that live on the first I qubits. There's not too many vectors, size S is going to stay polynomial, and they all have efficient representation. Matrix product state of bond dimension at most B, and B is also polynomial. Such that the important property is that there's something that's pretty close to the ground state, 1 minus delta, this is the delta parameter, and this thing that's close to the ground state, if I look at the left half of it, it's reduced density on the first I qubits, or think of the Schmidt vectors on the first I qubits, then these are not quite among my set, but they're in the linear span of the set.
Is there any relation between the tensors corresponding to different vectors in this set?
No, doesn't have. And they could definitely be linearly dependent. If they are, I could always prune it. I mean, do some, I could assume they're linearly independent, but I'm not going to worry about it. So there's not any general relation.
And the relation between Si and Si plus 1 also not at this point.
So I'll explain exactly. So I'm going to explain how to go from Si to Si plus 1. So that's the main observations. I mean, there's two simple important observations. The first observation is that constructing this for I equals 1 is easy. So if I take S1 to be what? I'll take S1 to be the set of all vectors, a basis, let's say like this. So what I mean by this is I just mean a basis for CD. Then the claim is that, I guess this is just practicing with the definition, then S1 is 1, 0, meaning very good. Bond dimension is 1 or 0, I don't know what you call it. And then the size, there's going to be D vector variable. Is this clear? Because, whatever my approximation to the ground state is, it has a reduced density on the first qubit. And that reduced density on the first qubit is supported on the space on which the first qubit lives, right? So if I take a basis for that space, I'm sure that I'm good. Is that okay? Or I see some puzzle looks, but it should not be. It should be okay. So.
What is the last component? Is D?
It's the local dimension of the qubit. So I just took a basis for CD, and this is it's the size of the set, the number of vectors.
So it's not the bond dimension.
No, the bond dimension is the one before. I put a 1, so I don't know if you can see from where you are, but B is the bond dimension. And so I mean bond dimension is 0, right? I guess you could call it 0.
But I thought that the qubit was defined by your system, so you don't have control over that.
Sorry?
I mean the qubit, right?
Yeah.
It's a qubit.
Yeah.
But that's fixed, right?
Yeah. So
it's
D is
given,
fixed. Yeah.
It's given by the problem.
Yeah.
So why do you list it among the parameters? Oh, you mean that the size
No,
of the first
this is for this set. This set has this value for S.
Oh.
This is the last number is always going to be the size of the set. For that particular set, the size happens to be D.
Okay.
Which is given to me.
And why is it D? Why is it?
It's a basis for CD. My set is a basis for the first qubit. The first qubit has D dimensions, so it's E1, E2, E3, which is canonical basis.
So D to the I you could always achieve if you want.
Exactly, right. I could generalize this, that's a good point. I could generalize this to say that I could get a set of size d to the I and all these parameters being very good. Of course, d to the I when I is n is exponential, and we don't include that. So essentially, the second observation is that given Sn, which is, suppose I was given Sn, which is, let's say, so n, and then let's say 1 over n cubed, and then I have poly bond dimension and poly size and variable. We are done. If I have this, right? Because then, in that case, what does it mean for set to be viable when I have the whole chain? Well, it just means the reduced density on all qubits. I mean, that's just gamma tilde. So I have a good approximation to the ground state, which is supported on the span of my set. In that case, I'll just be able to find it by minimizing the energy over the span of my set, which I don't want to write this too precisely, but you can write this as a convex program. You can solve this efficiently in time polynomial in the size of your representations and the size of the set. You'll find the vector in that span that minimizes the energy. And given this delta, I'll get a good approximation. Approximation, yeah, delta divided by gap. So there was a question. Sorry.
Does the algorithm require you know what delta ahead of time is?
What, sorry?
Do you need to know what delta is ahead of time is in order to actually do this, or?
By delta, you mean the gap?
Yeah.
Yeah.
Okay. But you can keep.
But just because it's
running it, right?
If I have a lower bound on the gap, this is fine. It's just you saw how it scales with the size of the gap. As the gap gets smaller, the algorithm takes much more time. So when I set my parameters in the algorithm, I need to say the gap is at least that much, so that I need to only consider things of that size, and we'll see that later. So if you have a lower bound on the gap, so you can always try. I mean, try a lower bound, see if it works or not.
So it's not so clear to me that you can optimize the convex programming, because it's a complicated object, right? It's this tensor, like this matrix product thing. So it's not just a single matrix.
Yeah. So what I look is that I look for a density matrix that's supported on the space. And the fact that it's supported on the space means that I can write it as a linear combination of all these matrix product states, so what I do is I'll actually, the variables of the convex program will be the energies of these individual matrix product states, not the matrix product states itself. But here I'd like to ask you to just believe me that you can do it. It's not completely trivial, but if you write it properly, you can do it. No, I could write anything. So given a set which is like this, let's write a delta. Then my procedure, what I'm describing, what you can do is we are done. What I mean by we are done is we can find gamma tilde such that the overlap, so it depends what you're interested in really, but such that the overlap with the ground state will be at least whatever this was by your gap. So, if you're interested in a constant approximation, yeah, you can set delta to a constant. The reason I'm setting it to be 1 over n cubed here is that as we go through the stages of the algorithm, it's going to be important at various points to have deltas which are inverse polynomial in size, even if at the end you're only interested in a constant approximation. This is this sort of fridge procedure that will make that smaller. This is just so far it's a definition, right? And the definition says that, if a set is viable, then there is a good approximation to the ground state which lies in that set.
But you don't know, right? You don't know.
Oh, so I'm using the gap. I'm sorry. Yes. So if I minimize the energy over my set, because of the gap, the vector that I find is necessarily going to be a good approximation to the ground state, given that there was one in there, of course, right? So my promise is saying that I can find a state that has low enough energy.
Yes, you didn't mention uniqueness.
I didn't mention it, but I guess you're right. You're right. So I am using uniqueness and the. I'm sorry?
It's possible that you have exact space instead of ground state. But that exact state also have a gap above it.
No. So my assumption is that there's a unique ground state.
Yeah, but
And there's a gap above that.
Yes, but it's possible that you did not get, you don't get the real ground state, but instead you get an exact state. That's a local minimum.
Local minimum of what? So,
So you get an excited stage instead.
no, I'm not going to get it.
I know, that's it.
Okay. But I don't know how to answer the question. Maybe you know how to answer it.
No, I'm waiting to hear.
Now, some algorithms could find an eigenstate separately.
Yeah, I mean, that's a guarantee of our algorithm. It's going to
Right.
find, it's going to work. It's going to find
You just have to show them the algorithm.
Exactly.
Yeah, okay. Okay, so maybe as we go, it'll be clear. Okay. What I did want to say here is that sort of this haystack procedure, it's easy to get started. And if we manage to make it till the end while keeping all the parameters under control, then we're in good shape. And then this is what I have to explain to you, how we build these sets from left to right. And maybe, well, okay, I can write it here. So there's going to be 4 steps. 2 of them are interesting, 2 are trivial. So I'll say what the 4 steps are, and then I'll focus on the 2 interesting ones. So here's the iterative step. So what we'll start with, I'll just assume that I have a set which has these qualities. So 2, B0, S0. These B0, S0, they're fixed polynomials in n. I mean, if you want to just think of them as being n cubed or n to the 4, we'll see as we go what they are. Right? But I assume that I have such a thing, and I'm going to make it better in 4 steps. So the first step is the fridge, is in saying, look, here you have a set. I mean, all things are good except the quality of the approximation, a half. This is kind of a little bit tight. I want to make this better. So we have a procedure that's going to transform such a thing into something that still lives on the same space, but now has much better approximation. At the cost of increasing these parameters. So that's the procedure that I call the fridge, or it's called also AGSP. The idea is going to be to use the Hamiltonian, use the local Hamiltonian, from it, construct a local operator, an MPO, that you're going to apply to all the vectors in your set. And it's going to have the guarantee that if these vectors contained a half approximation, as you apply this MPO, they'll contain better and better approximations. But applying the MPO will have a cost. It'll blow up the bond dimension, it'll blow up the size by polynomial factors. So the other steps are going to improve that. Actually, not quite yet. The next step is sort of a trivial step, which is going to increase, add 1 more qubit. I'll now consider vectors over, I have to make progress towards the right? I'll keep the same approximation quality, I'll keep the same bond dimension, and the only thing is that the size will, again, increase a little bit. Think of this as just doing the same kind of trivial thing as we did here. I just take all my matrix product states and I add a basis for the next qubit to all of them. So I multiply my size by d. This is really easy to do. It's trivial. I just couldn't afford to do it at every step because I can't multiply the size of my set at every step by d. I'll get something exponentially large. So the next 2 steps are trying to get us back to things under control. So the first one is another interesting step. So it's the fire step, or the, what did I call it, decoupling step. This is going to use the 1D structure and the gap and the area law to drastically reduce the size of this set at the cost of messing up, unfortunately, the nice approximation we had. So it'll bring it back up to some large constant. These bond dimensions will go up even some more, but the size will go down to the original size. So that's what this step is doing, right? I had a big set, contained a very good approximation, but I have a way to set things on fire, reduce the size by a lot to something of constant size. This will really use the fact that as we're making I'll say more about it later. And then the last step is, again, an easy step, is just reducing the bond dimension. So I'm just going to trim these vectors in a very naive way, just cut off the large Schmidt coefficients. I'll lose a little bit in the error, but I'll be able to bring things back to the same status as they were before. That's step D. So if we're able to carry out these 4 steps, we can go from here to here, and we're done, right? And what I'm claiming is that this step is trivial. I think maybe most of you can see it. I'm also claiming that this is pretty trivial. Just cut the bond dimension. You use the fact that, well, you have to say why you can afford to do that, but I'm not going to go into it. It's exercise. So the two interesting set steps are A and C. And I think A is the most interesting step here because it's the part where you're not doing exhaustive search. You're doing something smart. This is exhaustive search, just adding a qubit, anything to it. This is guided search. It's saying you have a reasonable approximation, you're making up a much better approximation. This is, so let me say something about this, and if I have time, I'll also say something about this.
When you said that the Hamiltonian was local, does that mean nearest neighbor?
Yeah. So I guess you could, I mean, if it's 2 or 3, I mean, if it has finite interaction length, then I can always block stuff. But I don't know how to, if it's something that's decaying, then I don't know what happens there.
What is B0 and S0? Like
they're fixed
constants?
They're universal polynomials. No, polynomials in N.
No.
So I could write the formula. They look a little bit like the parameters of the algorithm. So B0 is something, think of it as being N to the 2 to the 1 over delta. And S0 is something. They're just set to that.
So already in the second step, you are increasing it to those, and then you
no. Because in the second step, my things live on the space of dimension. Yes. I mean, naively, yeah, because anyways, it's going to increase later. I mean, it's not like I'll save much by improving the second step. Yeah. I think I'll have time to say something about A, but maybe not about C, unfortunately. But let's see A, unless there's other questions. All right. So how do you improve? In particular, this step relies on the gap and the local structure, but not one dimensions. So it's something that you can extend to 2 dimensions or more. So maybe it's an interesting object. So suppose you had the following. This is sort of your dream object. Suppose there exists some operator K. So an operator that acts on the whole chain. It's positive and it has 3 properties. The first property is that when you apply K to the ground state, you keep the ground state. This is the thing that we call approximate ground state projection. So it leaves the ground state invariant. Then it has the property that if you take any psi that is orthogonal to the ground state, so any excited state in particular, such that psi gamma is 0, then the norm of K applied to psi, this is at most inverse polynomial, let's say 1 over n cubed times the norm of psi squared. So it keeps the ground state invariant, it shrinks the other states. So it's probability 1, probability 2, and probability 3 is that K has a matrix product operator representation with small bond dimension. Let's say, I'll just write poly n bond dimension. So I want to claim that if I have such an operator, I can accomplish step A, and then I want to tell you how to get such an operator from the local Hamiltonian. So what's useful to note is that if I apply K to even something that's an approximation to the ground state, then this operator, okay, I should write it like this, then this operator, and then I look at what's the state, I look at the overlap with the ground state, then this is going to be bigger than, I don't know what the numbers are exactly, but let's say 4, probably this is okay, 4 over n cubed, right? If gamma tilde gamma is greater than the half. So if I start with a vector on the whole chain, right, that's a good approximation to the ground state. I apply K to it. The component of that vector that is on the ground state is left invariant, and the component that's orthogonal to the vector gets shrunk by a huge factor, 1 over n cubed.
These are always normalized. There's a normalization. So.
Yeah, they're normalized. I'm sorry. So I should divide this by the norm. Thank you. This is always normalized, but this one I should have been more careful given the norm, right? Okay. So that just follows from the first two properties. And now the claim is that, so, okay. The claim is that if I define, I'm going to tell you what the new set is now. This SI, let's call it SI prime. Let's write it like this. I'm going to write it as applying the operator. I'll tell you what this index is afterwards. And then I had a red pen. To the vectors that were in my set. Right? For every vector, so these are the vectors that are in the original set Si. And to each of them, I apply these operators. So what are these operators? Well, what I want to do is really apply the whole operator k, but k is an operator that acts on the whole chain, the way I defined it. So if I start with something like this, and I want to apply my MPO, well, it's fine, except the MPO sort of continues, right? And it's kind of asking me, well, what do you plug in here? So the way to apply such an MPO to a vector that stops here is simply to cut the MPO, look at the different values that this bond can take, and that's my index j. And so this here is kj, which is something that only acts on the left half of my chain. I have as many kj's as the original operator had as the bond dimension of the original MPO. And I'm going to apply every single one of them to my vectors. And so maybe you can see that if the original set, if gamma tilde was supported, the left half of gamma tilde was supported on these vectors, then the left half of k applied to gamma tilde is supported on the span of all these vectors. So all the vectors that I obtain by taking any vector in Si and applying any of these kj operators to it. So this set has the required properties. The approximation quality has improved to this number. I mean, I could just make it better if I wanted. What happened to the size? The size got multiplied by this bond that I had to cut, which is a fixed polynomial. I mean, that's the promise that I'm giving you. And the bond dimension has also been multiplied by whatever the bond dimension of my MPO was. So these parameters, the parameters B prime and S prime that I get here, they're both B0 and S0 times whatever the bond dimension of this MPO is. And as long as this is reasonable, I haven't blown up by too much. The next thing is I just want to give you an idea of where this MPO comes from. Is that okay?
So there is something unsettling about that slightly, that chain does not continue to the end, whereas the bottom does continue to the end. So
right.
Is it like a problem or?
No, I think no, it's not a problem. It's just a minor technicality. It's just the way I'm going to show you how to construct this operator k. It's natural to think of it as acting on the whole chain. Now you want to make it act only on the half. So you're just cutting in the middle and taking all possible values for whatever could be coming from the right-hand side, which is why I'm sticking in any possible index j here to the right-hand side and considering all cases. So that in a way I'm saying whatever the right-hand side was, I keep my approximation.
So how do you find k?
Yeah, so I'm going to define. I guess this is probably the last thing I'll do. But 5 minutes is enough. So it's a simple construction, but maybe it's useful. It's constructed directly from the local Hamiltonian. So if this was not completely clear, maybe just let's see how we can construct an operator that has these properties. So let's look first at this. So let's take parameter m and let's look at this operator now. So I'll look at am, which takes the Hamiltonian, it scales it by n. It looks at identity minus. So this is between 0 and 1, right? Because there's n terms and each of the terms has norm at most 1. So this is positive. I'm going to scale it, so there's a little bit of a scaling. Scale it by 1 minus the smallest energy by n. This is the scaling. And then I raise this to the power m. So the first thing, this is just a definition, right? Another way to, I mean, this is, well, okay, let me not say that. First, I want to show you that this operator satisfies the first two properties, but then it doesn't look like a reasonable MPO, and we'll have to do something to fix that. But let's first just study the first two properties. So let's look at what's the effect of AM on the ground state. Right. Well, first, the ground state is going to be an eigenvector of this, just because this is identity, it's an eigenvector of H, and that's the only things that I'm doing. So the only thing I have to do is compute the eigenvalue. And what's the eigenvalue is going to be something raised to the m. Then I'll have 1 minus E0 over n, because it's the ground state, times 1 over 1 minus E0 over n. Almost time for the wine reception. Gamma. So this is good, right? And now if I take psi, which is orthogonal to gamma, let's say to simplify, let me take psi such that it's one of the excited states, right? So such that psi h psi such is an eigenvector of H with energy E1. So in that case, AM psi, just because I'm assuming it's an eigenvector, just for simplicity, I'll get psi. And then what do I get inside my brackets here? I still have the normalization, 1 minus E0 over n, except that this term now is 1 minus E1 over n. E1 is at least E0 plus delta, so I'll get something like this. And then you can see that this is, how this behaves is basically like, I'm not going to do the calculation, but it's basically something that behaves 1 minus delta over n to the m.
It's the whole thing to the power n, right? To the line before.
Yes, thank you.
So you need to know the value of E0?
No, I need to know the value of delta
And the m
to
parameter.
set the m parameter. I need m to be at least n.
But it's in the definition of EM.
Right.
Yeah, you're right, but it's in a way, this is just a global scaling, right? I could just pull it out. It's just a constant that's outside. So if I think of keeping vectors that are normalized, have norm 1, then this actually doesn't really matter. It's a multiplier. So if I choose the wrong one, there'll be a multiplier here and the same multiplier here, and up to normalization, it won't really matter.
Well, just, I mean, you can choose the minus HT, right?
Yeah. Yeah, this is roughly what this is doing the same way, except this one I know how to think about in terms of making it into an MPO that has small one dimension. I think if you want to think of this as e to the minus beta h for some good choice of beta, and then what I'm going to do right now, think of it as being trotterization, then it would be the same. I find this easier to state, but if you're used to other things, yeah. So, but I should really tell you how to think of this as an MPO, and then we'll be done. Because there's just one nice idea there. So what is this? I can expand it, right? And I can write AM as, so there's this constant in front, 1 minus E0 over n to the m. And then I can expand this summation, and I can write it as the sum over terms. And what do the terms look like? This here, I want to write as 1 over n times 1 minus h1 plus 1 minus h2 plus 1 minus hn minus 1. Let's go to hn because I put an n. I don't want to. It should be n minus 1, but it's okay. So if I expand this summation, I get products of terms, which look like 1 minus, could be anything, right? 1 minus hi1, 1 minus hi2. I have m of them, 1 minus him. And these indices I1 up to Im, they range in 1 to n, right? So I just expanded. So this is what my operator looks like so far. It's a sum of many, many terms. And what do these terms look like? Well, what does this, let me call this P, I1, they look like terms like this, PI1, and then maybe the second one, PI2, is maybe something like this, PI2. Then maybe PI3 is here. Maybe I have PI4 is here. And this is the operator that I'm trying to apply to my vectors. It just has all these P, which are 1 minus h, they come from the Hamiltonian, they're local terms, and they're arranged in an arbitrary order. So if I think of this as an MPO, this maybe has very large bond dimension, because some of the terms in that sum involve, for instance, PI1, PI2, then PI1 could be the same again. And I could have a long chain like this of M, and my M is N. So I could have one of the terms in here is a long chain that has all these projections that keep acting on the first two qubits over and over again, n times. So the bond dimension of this would be something like d to the n. It's exponential so far, the dimension. If I represent this naively as an MPO, it has exponential bond dimension. But the observation is that this is not typical.
Thomas, there's a normalization factor, 1 over n to the n.
Oh yeah, I forgot that. Sorry, thanks. Yeah. Another normalization. Yeah. The observation is that there's many terms in here, and some of them are bad. Like this 1, 2, 1, 2, 1, 2 term has a huge bond dimension. But there's many terms, and as Lev just pointed out, these terms are scaled by a very small factor. So as long as there's few terms that have huge bond dimension, I can remove them and approximate this operator by only terms that are better behaved, that look like something like this one, such that across any bond, I only have a constant, or at most logarithmic, if I want to keep a polynomial bond dimension, logarithmic number of projections that act across any one bond here. And this is what we're going to do. We're going to think of this as a superposition over exponentially many terms, and use these something called a matrix Chernoff bound to sample. We're going to say this operator is well approximated by taking a polynomial size number of these terms uniformly at random among all possibilities and renormalizing. So the claim, and I'm really over time, so I won't state it precisely, is that for our purposes, AM is well approximated by the appropriate scaling times the sum of these things, 1 minus hi1, etc., up to 1 minus hin. The sum over what? Now, not all possible indices, but just a random poly-size subset of indices. And this approximation is an approximation in operator norm, up to an error that I can make inverse polynomial if I want. So that's what's known as a matrix Chernoff bound or concentration bound for sums of random matrices. So that's going to be the MPO. This is going to be K. The last thing to check is that if I take only polynomially many of these possibilities, the chance that I get any one which acts too many times across any given bond is sufficiently small that I can basically consider it's not going to happen. I mean, if it happens, let's say I sample again. So you get a randomized algorithm.
So, quick question.
So, yeah.
You said this follows from a random matrix theory result?
Yeah.
But
well, it depends what you call random matrix.
So I thought you said it only... I thought I heard you say that approximate equality is because of a random matrix result.
Yeah, matrix Chernoff bound.
So, but you don't assume that your local terms are necessarily random.
No, not at all. I think of this product here as a random variable. My sample space is all possible values for the product, and the random variable takes this value with probability this number, and that's random. Right. Of course, the Hamiltonian is not random. I mean, this works for any Hamiltonian. Good point. Thanks. Okay, so I should wrap up. I told you what ingredient number 1 was. Then I'm sorry I don't have time to say. So this was the procedure that lets you, the fridge, that lets you improve the quality of your set. The procedure that's missing is the fire that reduces the size of the set. This is an idea that was already present in earlier exponential time algorithms for the same problem. It's called this decoupling. It uses the fact that this is a one-dimensional chain to say that once you've progressed up to here and you have all these set of candidate solutions, what's important about them? It's not how they look up to here. What's important is just that they can be extended. You're going to be able to make progress. They can be extended into a state that has a low enough energy. And whether something that lives on here can be extended to something that has a low energy only depends on how it looks like at the boundary. And let's say it's total energy to the left, right? But it doesn't depend on how these tensors look like here. So there's a pruning step. This is the step I didn't explain. This decoupling step does some pruning to say, among my huge haystack, I only need to keep one possible candidate for every way, every possibility for how the contraction up to here looks like in big terms. And this lets me cut down a lot because there's much fewer contractions than the size of my set. There's a fixed number throughout the algorithm, which is the dimension of my space, the bond and the local dimension, polynomial. I'm skipping a lot of details, but I'm really over time, so I should stop if there's any questions. Well, there's a reception coming up. Yeah.
So does your algorithm give bond dimension D by the time you get to the end?
D or B or?
D.